This example problem uses Newton's second law for rotation to determine the acceleration and the tension in the string of an Atwood's machine. We're given the masses, and we're told that the pulley is a solid cylinder, and we're given its radius. We're going to look for three things. We're going to look for the two tensions and the acceleration. But before we do that, we're asked the question of why must the tension in the cord connected to the boxes be different? Well, if you think about it, if they have to accelerate at the same rate, and we know that block A is more massive than block B, that tells me that for them to accelerate at the same rate, that tension connected to A must be greater than the tension connected to B so that it would have the same acceleration as B. We'll see that as we write net force equations for these two things. As we learned in class, when you have things that move linearly, you're going to do free body diagrams. And when you have things that rotate, you're going to draw force diagrams. So let's start with our free body diagrams. Our free body diagram for block A has the tension T1. That's the one that'll be the block, or the rope on the right is what we'll call T1. And it has FGA acting on it downward. And off on the side, I always like to show the direction of acceleration. And block A is going to be accelerating downward. For block B, it also has a tension upward, but this time it's T2. And we also have a force of gravity acting downward. This block's going to accelerate upward. I know the direction of these accelerations just by thinking about my problem, realizing that block A is more massive, therefore will go downward while block B goes upward. And then lastly, I have the pulley. We know that there's a gravitational force acting in the center of our pulley. And we know that there's also some force holding the pulley upward. I'm just going to call that an applied force. Those both act at the axis of rotation. And then there are two tensions, and we draw those tensions at that point where the string leaves the pulley. So we have T1 pulling it downward on the right-hand side, and T2 pulling it downward on the left-hand side. I've now drawn my two free body diagrams and my force diagram. And so I'm going to write some net force and net torque equations based on these diagrams. For block A, I have T1 upward minus FGA minus because it's downward. That's going to be equal to negative massive A times acceleration. Negative because it's pointed downward. And I left off the subscript A on my acceleration because both A and B are going to accelerate at the same rate. That's always true as long as you don't have a stretchy string, which we'll always consider all of our strings to be non-stretchy. For my second free body diagram, I have T2 minus FGB, and that equals a positive MB times A. And then for my force diagram, I'm going to write a net torque equation. So this time I'll look at all the forces creating torques. And I see that applied force, the thing that's holding the pulley up, as well as the gravitational force on the pulley, those two forces act at the axis of rotation, so they do not exert torques. So I simply have the torque from tension 1, and I'll leave the vector symbols there. I'll think about direction later. And the torque from tension 2. And those two torques added together equal I times alpha. And again, putting a vector symbol on top of alpha, because I have not yet thought about direction. So plugging in some other variables I know, working with my first equation, I have P1, and I know that I can calculate the gravitational force by doing mass times gravitational acceleration. Likewise, in my equation for block B, and then working with my torque equation, I'll focus on those directions and writing out the net torque. I think I'll need a little more room, so I'll do that down here. So for starters, that torque 1, we know that torque, the magnitude, is equal to FR sine theta. So the torque from tension 1 would be T1 times the radius of my pulley R times the sine of 90 degrees. It's the sine of 90 degrees because 90 degrees is the angle between my radius and tension vectors. Now, if I look at my force diagram, if T1 were the only force acting on my pulley, it would cause a clockwise rotation, and we consider clockwise to be a negative. So I'll put a negative sign in front of that. And then for T2, tau 2, my torque caused by my second tension, I have T2 times R times the sine of 90 degrees once again. If T2 were the only force acting on my pulley, it would cause counterclockwise rotation. That means it's a positive torque. The moment of inertia for a pulley is 1/2 mass, and I'm going to call this same variable given to me, which I believe was MC, times radius squared. So there's my moment of inertia, and I multiply that by the angular acceleration. Looking at my pulley and looking at my system in general, I know that A is going to go downward and B is going to go upward. That means this pulley has to be rotating, really accelerating in the clockwise direction. So that means I must have a negative acceleration. I'll put that negative sign out front here in my alpha. So now I'm down to having 3 different equations. Here's equation 1, equation 2, and equation 3 over here. My unknowns are T1, T2, A, and alpha. I'm given numbers for everything else. I only have 3 equations. That means I can only have 3 unknowns. But there happens to be a relationship between alpha and A, linear acceleration. Mainly the alpha is equal to A over R. I'm going to use that relationship between the quantities to solve for what I'm looking for here. I'm going to plug that into my torque equation. Negative T1R, we know that sine of 90 is 1, plus T2R, again sine of 90 is 1, equals negative 1/2 mass of my pulley, radius squared, times A over R. Now I have 3 equations with the same 3 unknowns, and so the rest of my work is algebra. Before I do that algebra, I'll notice that this R cancels out with the squared here. And also, I'll then notice that there's an R in every term in my torque equation. So that means that if I divide both sides of my equation by R, this R, and this R would all cancel. Let's write that torque equation one more time, taking into account all these things that we've canceled out. I have negative T1 plus T2 equals negative 1/2 MC times A. If I take equation 1 and 2 from above and solve those equations for T1 and T2, I can plug those into my torque equation. So equation 1 would give me T1 equals MA times G minus MA times acceleration. And equation 2 would give me that T2 is equal to mb times g plus mb times acceleration. Plugging those two expressions into my torque equation, which again, I'll call that equation 3, looks like this. I say negative, and in parentheses, mag minus maa plus mbg plus mba equals negative 1/2 mca. Now I only have one variable in my equation, so I'll need to rearrange my variables to solve for that one unknown. So first I'll distribute this negative. Negative ma times g plus ma times acceleration plus mb times g plus mb times acceleration equals negative 1/2 mc times acceleration. Then I'll get all the terms with acceleration onto the same side of the equal sign, and anything without acceleration onto the other side. So to do that, I'm going to add the mag and subtract the mbg from the other side, and then add this term to both sides. So I end up with ma times acceleration plus mb times acceleration plus 1/2 mc times acceleration. And that is equal to ma times g minus mb times g. Then I can factor out the acceleration from the left-hand side. So I have ma plus mb plus 1/2 mc times acceleration. I can also factor the g out to make things simpler, although it's not necessary. And I'll do it here. ma minus mb times g. And then my last step, acceleration is equal to ma minus mb times g all over ma plus mb plus 1/2 mc. Here's what I get when I plug some numbers in. I'm told that ma is 12 kilograms and mb is 8.5. I have 12 kilograms minus 8.5 kilograms. And we know that g is 9.8 meters per second squared. And again, in the denominator, I have 12 kilograms plus 8.5 kilograms plus 1/2 times the mass of that pulley, which we're given to be 20 kilograms. When I plug all those numbers into my calculator, I end up finding an acceleration with the magnitude of 1.12 meters per second squared. That was my answer to part B of my problem. Once you have that value, finding the tensions is relatively straightforward because I have two equations for those tensions. Here's one of those equations for T1, and here's the other equation for T2. All I have to do is plug in the numbers for A and the numbers that were given for the masses into these two equations, and I find that T1 is equal to 104 newtons and T2 is equal to 92.8 newtons. If you have any further questions about this problem, feel free to come and talk to me about it.